Could we go to the full screen mode?
Okay. Yeah, is it okay?
Yeah, it's perfectly
Yeah.
fine.
Okay.
So yeah,
Perfect.
so it's a pleasure to have Dr. Ryotaro Suzuki here, who is just starting off his PhD at the Free University of Berlin. I think I'm right. He just yeah, he just finished his master's at the Graduate School of Engineering at Osaka, and then he decided to move all the way to Germany and start his PhD at the Freie University of Berlin. So we are all excited to have you here, Ryotaro. So I, I think I give you the stage. We are very excited to hear your talk. Please.
Yeah, thank you so much for the introducing myself. Hello everyone, and first I'd like to thank organizer to inviting me to this super exciting workshop. Today I want to talk about computational complexity aspect of dual unitary quantum circuit. So I feel my topic is a little bit different from the topic discussed so far, but I hope it will be interesting for all of you. And yeah, as I introduced, I studied this work when I was at Osaka University, and this is in collaboration with Kosuke Mitai and Keisuke Fuji, who are faculty members at Osaka University. And this presentation is based on this paper. Okay. So so because this work is about quantum computation, let me introduce briefly about what is quantum computation. So quantum computer is a computer which makes use quantumness, for example, superposition or magicness or something like that. And what we will do is first we prepare a quantum state for initial state, and we execute quantum operations such as unitary operators or measurement. And finally, we measure qubit to obtain computational outcome. So this is a abstract model of quantum computer. And it's known that the computer outperform classical computers, that's the conventional computers, for certain problems. For example, factoring problem. So given an integer, it's known that quantum computer can solve efficiently whether integer is a prime number or not. But classical computer cannot. And also, I'm going to talk only about circuit model in this talk. I briefly introduced that there are several models to realize quantum computer. So first model is a well-known circuit model, which we apply unitary gate sequentially. And another interesting model is a measurement-based quantum computation, where we prepare a quantum state firstly, which is an entangled non-trivial quantum state, and we measure each qubit adaptively, which means that according to the previous measurement outcome, we choose the measurement basis adaptively. And the another example is adiabatic quantum computation, where we change Hamiltonian adiabatically, and ground state perform quantum computation. And so next I will focus on this circuit model. So in this circuit model, for initial state, we arrange so-called qubit, which is an element of two-dimensional Hilbert space. And we apply unitary operators, and the computation output depends on the problem we want to solve. So for example, if we want to solve decision problem, such as a factoring problem, then we measure local observable. And the next answer problem is so-called sampling problem. And this is the exact problem where Google shows a quantum supremacy 2 years ago. And what we do is to sample from a distribution of wave function of final state. So if we perform some quantum circuit, then the final state have a coherent non-trivial get a non-trivial wave function, and sampling means that we sample one measurement outcome from this probabilistic distribution. And the classical paper show that there is a universal gate set of quantum circuit, which means that every 2 to the n unitary operator can be decomposed into these three unitary gate, so-called Adamar gate, T gate, and CZ gate. So in this sense, these operator code forming universal gate set. And it's also known that this CZ gate can be replaced by arbitrarily entangling 2-qubit gate. And so there is, and I want to mention one fundamental question about quantum computation. So the main question I would like to address is what makes quantum computation different from classical computer. So quantum computation can outperform classical one in certain problems. So what ingredient makes quantum computation different from classical one? Accordingly, when is quantum computation tractable for classical one is also interesting problem. So what I'm saying is in general circuit, it cannot be simulated efficiently in classical computer, but in some circuit, they can be simulated classically. So the difference between this circuit and this circuit is the exact ingredient for the difference between quantum computation and classical computation. And there are two famous examples for classical symmetrical quantum circuit. First example is for so-called Clifford circuit, where each gate are chosen from this unitary gate, and this unitary gate satisfy this condition. So if we see Heisenberg picture, this Clifford circuit is classically symmetrical because we can just follow the Heisenberg evolution of these power matrices. And another example of classical symmetrical quantum circuit is so-called match gate, where these gates are composed from this gate, which I will explain later. And where matrix A and matrix B are chosen from SU2 matrices. And it's not only interesting for theoretically, it's also important for application. For example, if we use quantum classical symmetrical quantum circuit, we can estimate error of quantum operators efficiently, or we can evaluate performance of error correcting codes efficiently. And more interestingly, because these classical symmetrical quantum circuit is easy to be simulated, it's natural to be related to exactly isoprobable model of non-equilibrium physics. So I want to explain briefly the relationship between exactly isoprobable model and quantum computation. So the interesting relationship is about between free fermion and match gate. And I note that match gate is discovered by computer scientists, and it is an independent interest of computer science. But after that, relationship between free fermion and match gate are discovered. So free fermion operator are given by this operator, and we map to Majorana operator. And using Joule-Wigner transformation, these Majorana operator, these fermion and Majorana fermion operator can be written by these power matrices. And actually, these match gate can be written by a Hamiltonian generator, whose Hamiltonian is non-interacting fermion, Majorana fermion. So for example, this XX gate is one of match gate, and they can be written by this Majorana operator. So match gate can be written by dynamics of non-interacting free fermion. And in this talk, dual-unitary quantum circuit is a new interesting exactly solvable model. So I studied the quantum computation counterpart of this quantum circuit. So this is my research outline. So first, regard dual-unitary quantum circuit as quantum computation, and next we identify their computation power in terms of computation complexity of local observables and sampling complexity, and then generalize the model to 2 dimensions. So first, let me explain the definition of dual-unitary quantum circuit, which were explored by these very nice papers. So dual-unitary quantum circuit is a brickwork quantum circuit arising from certain initial states I will define later. And these unitary gates are defined by this property where if we shuffle this unitary gate, then of course these are unitary, so they define this unitarity, but if unitary satisfy this unitarity in space direction, this unitary is called dual unitary gate. And it's known that the general form of dual unitary quantum circuit is written like this. So these are arbitrary 1-qubit gate, and this is a swap gate, and this is a CZ gate I explained before. Yeah, so exact solvability of dual unitary quantum circuit is actually very interesting because this gate include 1-qubit gate and CZ gate, and at first sight it can perform universal quantum computation, but it's exactly solvable. So yeah, at first sight it's very non-trivial for the solvability. And I explain the initial state where which makes dual unitary quantum circuit solvable. So the initial state is written by matrix product state, where the state is written by some matrices satisfying these 2 conditions. First condition is about the transfer matrices of A has a Bell pair eigenvector. And second condition is this transfer matrix has a unique maximum eigenvalue. And the simplest example of solvable initial state is the chain of EPPL. So let me move on to the computational power of the unitary quantum circuit. So first, we assume that the computational output is local measurement outcome. So in the end of computation, we measure local observable, and this will be a computation outcome. And in my problem setting, we fix the number of qubits n and determine the computation power in time t or depth t. So we divide our result into early time and late time. So in early time, more specifically, if t depth over time t satisfy this condition, then this dual unitary quantum circuit expectation value of dual unitary quantum circuit can be written by this. So it means that right cone is inside of whole qubit. And in this case, actually this local observable is exactly solvable because using this nice property or definition of dual unitary gate, we can eliminate these unitary gate accordingly, and we get that the expectation value is nothing but trace. So actually, the problem determining this local observable is in P, which means that it's easy for classical computer and even much weaker than classical computer because it does not compute anything because this output does not depend on any unitary. So the result can be generalized easily for general solvable initial state. So the expectation value of rho arising from a general solvable initial state is written like this. And the difference between the earlier one is only in this part. And to compute this transfer matrix, we use first condition 1, which means that this pair is eigenvector of eigenvalue 1. And by definition of condition 2, it is a unique maximum eigenvector. So it means that and power of this transfer matrix, it looks like a Bell pair, project of Bell pair, and the error term is suppressed exponentially. So by using this observation, this expectation value can be written like this. So this is the error term, and we can compute explicitly this term because by using this definition or condition, we can eliminate this upper end term of matrix A and this dual unitary gate sequentially, and we get that the expectation value is traceable. So we have shown that the log observable in early time is classical simulable. So what about late time? So in late time regime, the expectation value can be written graphically like this, and actually we cannot remove top and bottom unitaries like as with the previous case because they are not connected by identity operator. So my question is it still simulable? And it turns out to be no unless classical computers are as powerful as quantum computers. So let me explain the detail. So first we note that this dual unitary quantum circuit can construct universal gate if there were no swap gate. So if there are no swap gate, then it has arbitrary 1-qubit gate and it has arbitrary CZ gate to the power of alpha. So what we will do is to remove swap gate from this dual unitary gate. And we can simply remove swap gate by using this some subsystem of quantum circuit. So if we sequentially perform swap gate, and at some point we perform some non-trivial dual unitary gate like a CZ gate, then this CZ gate, then this quantum circuit can be equivalent to this circuit, which means that almost all gate is equal to identity gate, and only one gate is for example, CZ gate. And it's well known that CZ gate plus arbitrary 1-qubit gate can perform universal quantum computation. So in high depths, like if T is some polynomial of the number of qubits, then dual unitary quantum circuit can perform universal quantum computation. So it means that if this dual-unitary quantum circuit can implement arbitrary quantum algorithm, and so it's unlikely to be classically symmetrical. So let me summarize the result. In early time, in linear depth of some in linear depth with coefficient 1, the expectation value is nothing but a trace O, close to trace O, and which means that this is a classical symmetrical. On the other hand, at a high depth, dual-unitary quantum circuit implement arbitrary quantum algorithm. That's why they can perform universal quantum computation. And the interesting is that in early time, it is a early time, but it's a linear time of number of qubits. So the entanglement spread of for quantum systems. So it means that the classical symmetricity of this linear time is very non-trivial. And actually, there is no so far there were no such classical symmetrical model where they are classically symmetrical in some polynomial time and they can perform universal computation at higher time. For example, in Clifford circuit, they are classically symmetrical in whole polynomial time and they never perform universal quantum computation. And Matchgate is likewise. So so dual-unitary quantum circuit is a very unconventional classically symmetrical quantum circuit. And next, I want to move on to the sampling complexity. So the problem of sampling complexity is to sample output of dual-unitary quantum circuit up to multiplicative error. More specifically, the output distribution is defined by if we perform dual-unitary quantum circuit and measure in 0 or 1 basis, then this output probability is output of dual-unitary quantum circuit. And my question is there a classical computer whose output satisfies this multiplicative error closeness? And it turns out to be the classical sampling is hard due to this observation. First, let me introduce that sampling from measurement output distribution to the cluster state is known to be hard by classical computer under some computational complexity assumption. 2D cluster state is defined by on a two-dimensional regular lattice, and first we prepare a plus state, which is a plus one eigenvector of power x, and then apply z-gate act on all nearest neighbor site. So after applying z-gate, they are called to the cluster state. And actually, 1D dual-unitary quantum circuit can generate a state which is equivalent to the cluster state. So by using this carefully constructed dual-unitary quantum circuit and rearranging the size of qubit, it can be shown that this is equivalent to the cluster state. So combining these two results, we can show that classical sample of dual-unitary quantum circuit is hard problem. So next, I want to generalize the model to 2 dimensions.
Sorry, I have a stupid question. So I don't understand. So the cluster state is a 2D state, and here you have a 1D dual unitary circuit. So I don't understand in what sense you can generate a 2D cluster state in the 1D setting.
Yes. I rearranged this. So for example, this is a 1D chain, and if we divide this chain into some number of blocks and rearrange, for example, this is this site, and the next block is rearranged to next one. And if we do this rearrangement, this qubit is connected to next subsystem, and this qubit is next to subsystem because of this gate. So in this sense, it's equivalent to 2D state.
Okay, I see. Thanks.
Thanks. So into two-dimensional dual-unitary quantum circuit, we define quantum circuit as following. So at even time, we perform dual-unitary gate, and at odd time, we perform arbitrary two-qubit unitary gate. So allowance of arbitrary two-qubit gate are big difference between 1 dimension and 2 dimensions. And the initial state is defined as following. So we define as a rows of initial state in 1D case. So we arrange 1D solvable initial state vertically. And it can be graphically shown that the local observable in early time is also classically symmetrical. So this is a sketch. So if we look at the edge of right cone, then these dual unitary gate are eliminated following this definition, and these arbitrary unitary gate can be eliminated by the definition of unitary gate. So by using this equation sequentially, this expectation value is close to threshold. And hardness is as same as 1D case. So let me summarize the result. So as with the 1D case, in linear depth, the expectation value is classically symmetrical, but at high depth circuit, because they can perform universal quantum computation, it's unlikely to be classically symmetrical. And we can, and because unitary gate acting at odd time can be identity, so we can generalize the square lattice into some another lattice, for example, honeycomb lattice. This is because honeycomb lattice is equivalent to this lattice, and if we act identity gate to this square lattice, then we can effectively remove this edge. So this dual unitary quantum circuit where we apply identity gate here is equivalent to this honeycomb lattice. It is a simple generalization. And I also consider the sampling complexity of 2D case, and this is much simpler than 1D case because we can just generate 2D cluster state by using 2D dual unitary quantum circuit. And what is interesting is because sampling problem of general quantum circuit becomes hard at depth 4, and also dual unitary quantum circuit becomes hard at depth 4. So in this sense, the hardness or sampling complexity of dual unitary quantum circuit is equal to general quantum circuit. So this is end of my talk. So in conclusion, dual unitary quantum circuit is a new type of classical symmetrical quantum circuit where computational complexity highly depends on circuit depth or time. And I think that might be related to computational phase transition, which has been recently studied extensively. And let me comment some future work. So one thing is I'm interested in computation power of dual-unitary control circuit with non-solvable initial state, where, for example, in Clifford circuit, it's known that there is a magic state which makes Clifford circuit stronger than without magic state. So I expect that there is a non-solvable initial state which makes dual-unitary quantum circuit more powerful. And I think the dual-unitary quantum circuit with open boundary condition is has a non-trivial effect for quantum complexity. And the final thing is I'm also interested in a relationship with other exact solver model and quantum computation. So in this sense, I'm recently interested in so-called quantum cellular automata rule 54, which is another model for dual space-time dual model, and I think that it's also another candidate of classical simulable quantum circuit. Yeah, so this is the end of the talk. Thank you for listening.
Thank you so much for a nice talk. I think the floor is now open for questions. So if there are any questions, you can ask now.
So can I ask?
Please go ahead.
So very nice talk. Yeah, very nice talk. So I have a question on the 2D case. So first of all, do you also have at least for the structure of the circuits that you have, do you have a complete characterization of the dual unitary gates, as in the? So if I understand correctly, here you use the 1D gates just arranged in a 2D settings, but in principle one can also imagine, say, four side gates, which are dual unitary.
Yes.
So did you look into that? And then the second question is here again. You used initial states, which generalize the 1D case because you put layers on 1D. I think a very interesting question would be whether there exists 2D states where the entanglement is not zero every other row. So something which is truly a 2D patch, say.
Yeah, I think that's very interesting question. As for the first question, I'm not completely classified, but I can say trivially that if we combine this dual unitary at this time and this unitary gate at odd time, so if we combine these 4 qubits as a one unitary gate, then we can say that these classical simulable unitary gate acting on 4 site. So by combining these gates at one unitary gate, then we can construct some non-trivial for example, 4 qubit gate.
But in principle, there might be more general
right.
4 side gates, right?
Yeah. So and yeah, as for the second question, I think we can generalize this to some non-trivial PEPs if we so
maybe we with some perfect tensor or something like that allows you to contract in all the directions. So this is something that it's very natural when you go from 1D to 2D. Yeah. So I was wondering whether you thought about this or not.
Yeah, what I did, one thing is to bounding this MPS together, and if we see it as one second MPS, then this second so-called pseudo 1D MPS can be if it has if it satisfies the 2 conditions, then then it satisfies the solvability. And if we decompose again the second MPS to some PEPs, then we can create some non-trivial papers that satisfy solvability. But I don't completely classify it. So yeah, that's interesting.
But thanks. This is it was very interesting talk. Thank you.
Yeah, thank you very much.
Are there any other questions? If not, let's thank the speaker for a very lovely talk. Thank you so much for coming.
Yeah, thank you.
Thank you. So we have the last talk of this session, and that is by Professor Boris Kutkin. So if Professor Kutkin is in the audience, maybe we can. Yes. So Professor Kutkin, are you in the audience? He is logged in.
Yeah. Boris is there. Hi, Boris. Yeah. Can you hear us? We see your speakerphone is on, but
speaker is on, but we can't hear him.
Yeah, we can't hear you.
I think we are running ahead of time by 5 minutes, so that could be the reason why he might have just stepped out or something.